This video lesson on the scientific method is geared to two types of folks. The first set of folks is those who have not been exposed to the scientific method at all. This would be their introduction to the scientific method and the first part of a two-part series on the method. The second type of folks that would be interested in this video are those folks who may have been exposed to the scientific method and have used it, but have been away from it for some time and may need a quick refresher. So those are the two types of folks that will get the most information out of this type of video. If you have followed any of my chemistry or science videos on various subjects, you know that I start out by first defining our concept, and this video is no different. So we're going to set our definition of what the scientific method is in the following slide. The method is a process of inquiry where we're going to use experimentation and discovery to explain some observations that have been previously made or to help us solve a problem. When we do it properly, the scientific method leads to strong explanations and conclusions about observations that have been made. However, the scientific method is not a one-shot deal. It is continuously used throughout science, engineering, process development to further refine, help further understand a problem, or make further explanations on observations made in the field. The goal is to get more and more information and advanced science knowledge, and the scientific method is a way to do that. In this slide are the sequence and steps that are used in the scientific method. Now, you may see some models with one or two more steps in the main step pathway here. Okay, here. But you need at least these 6 steps to be considered a valid scientific method model. This other feeder step here, the observations, I'm using to show you how it feeds into the question phase. But this could be previously made observations, or you want to understand something better, or there is a problem that needs to be solved and you don't know how to solve it right away, so you're going to have to do some type of scientific inquiry, discovery, to understand the problem so you can solve it, right? So let's look at these steps real quick. The first step is you're going to ask a question. Questions could be, let me give you an example. You notice from your observations that when you squeeze orange juice out of fresh oranges, some of the glasses of orange juice are sweeter than the others, right? And you want to understand why that is, right? So the question would be, why is it when I squeeze orange juice from fresh oranges do I get different levels of sweetness, right? The next thing you want to do is you want to do some background research on the sweetness of orange juice. What factors go into that? Could it be that the orange type? Could it be the orange size? How much time the orange was left to ripen on the tree versus ripen in the supermarket, right? The goal here is to understand as much as you can about the observations that you made and your question, and not reinvent the wheel. It costs money, time, and resources to run experiments. If somebody has already addressed and answered your question, that's better, right? If they've not, then you're going to look for ways to advance science by doing the next couple of steps, right? Once you have your data and your observations and your question, when I mean data, I mean your research data, you're now going to be in a better position to formulate an intelligent hypothesis, one that now should be able to address your question and answer it. The hypothesis is a statement. It is not a question. Generally, it's an if I do this, then this will happen statement. If I squeeze large oranges, the orange juice will be sweeter. If I squeeze California oranges versus Florida oranges, the orange juice will be sweeter. If I let the oranges ripen on the tree longer, the orange juice will be sweeter. Those are all testable hypotheses. The testable hypothesis means you need to be able to test the input by varying the variable, and the output needs to be tested with some type of metric that you can measure with a number scale and then be able to do analysis with it. Hypotheses that don't meet those criteria are not good hypotheses, right? For example, let's look at something like this. If I make a cake, she will love me. Or if I buy her a ring, she will love me more. There's no real way to test the amount of love, right? There's no love scale, right? What does it mean, love you more? Or Jack loves me more than Steve. There's no way to test that out. There's no love gauge that you can put on Jack and Steve to get a measure of their love for you, right? So it needs to be testable. Once you've done that, you're going to make your hypothesis and do experiments. The hypothesis and the experiments go together. You need to design an experimental plan or process so that you can test your hypothesis. So the experiment is designed to answer or prove or disprove your hypothesis. It's no good to do an experiment that doesn't address or prove or disprove your hypothesis. For example, back to the orange one again. If your hypothesis says larger oranges make sweeter juice, there's no reason to go in and test grapefruit or the same size oranges, right? You got to have an intelligent experimental plan and design. Last couple of things here real quick. You're going to analyze your data. Once you've measured your results, you've got to find a way to analyze it and look for trends. The trends will help you see whether or not there's a relationship between your input variable and your output variable, in this case orange size versus sweetness. And then once you're done that, you're going to report your results and answer the question, was your hypothesis correct? In this stage, and even this stage, there might be some revisiting because you may start generating data and realize, well, I need to test a different size orange now because I'm not getting enough information. Or I'm going to change my hypothesis now because I see that there's no correlation between this, and so I still need to understand what's going on. Or I may look at my analysis and say I need to do additional experimentation, or I need to do some other type of analysis to better separate the data. Now I'm going to go through each step in a little bit more detail, but I spent a lot of time on the previous slide talking about it, so I'm going to spend some additional time on each one of these, but not much. So again, our question thing is we want to understand what we want to learn. So we want to be, it's the how, why, when, what, where. And it's designed to advance knowledge in science, right? Or to solve a problem that we have on the process line or product line, right? This is the question is either based on observation you made or general inquiry. And here are some examples, right? And I'm not going to read them out loud, but you can see here that these are good questions. Why does this happen if I do this? What happens when I do this, right? What's the reasoning behind this? So these are type of questions that you want to ask based on the observations that are feeding into the question part. The questions really need to be to understand what the observations were. Again, in the background research stage, you want to not reinvent the wheel. So you want to understand as much as you can about the observations and how this would relate to your question. So you can do some research, either literature, online, ask colleagues, things like that. The goal here is to get a better understanding of the landscape, science landscape around the issue, which will help you hone your experiments and hypothesis and understanding of it, right? Don't reinvent the wheel, but learn from it to develop a better understanding of it and design better experiments to advance science. Some folks think that you need to have a hypothesis first as part of the scientific method, and then everything else follows. And that is far from the case. There's no way you can make a good educated hypothesis without doing all the steps we've done before, educating yourself on what the literature is as far as what is already known about the issue, the problem, or the observations. And then once you have a better understanding, how does that relate to your question, right? The goal of the hypothesis is now to take the information that you've learned and be able to create a testable statement that will yield information to help you answer your question or solve your problem. So again, this is a testable statement. It is not a wishy-washy statement. It's not a question. Often it's going to be an if-then statement. If I do this action, this will happen. If I hit the baseball hard enough, it will get a home run. If I squeeze the large oranges, I will get sweeter juice, right? And there are some examples here. Remember, the statement, your hypothesis statement, needs to be testable and address your question. If it doesn't, then it's not a good hypothesis statement. The experimental part of the scientific method is usually the one that is the longest. It takes the most resources, the most time, and it costs the most, right? It's when a bulk of the work is done, so the experimental plan needs to be efficient, reliable, and accurate. Otherwise, you're wasting resources. So when you design your plan, it has to have several key factors involved. First of all, it has to be able to test your hypothesis both ways, either negate it or prove it. Secondly, it needs to, if you've done your hypothesis testing, this is going to be an automatic. It's going to address your question and be able to answer your question through your hypothesis. Thirdly, it needs to have a control experiment in order for it to be a valid experimental plan. And what I mean by control, a control is a set of conditions that are run through the entire experimental plan that will give an expected result. Let's look at something real quick here. Suppose you are looking at a new process to make batteries, and the batteries that are resulting from this process are expected to give higher voltage yield or voltage performance at reduced weight. In order for you to test whether or not your process is working well, you need to be able to make sure that your testing equipment is operating and your process gives you the expected results. So let's look at it real quick this way. In order for you to test your measuring equipment, you need to test it with a known entity. So if you're looking at batteries and you're trying to make high performance batteries, maybe you test the current state of the art or the current battery on the test equipment to see if you get the expected results. If you get the expected results, you can assume that your testing procedure is going to give you reliable and accurate results. The next thing you want to do is, if you have a current formulation for the state-of-the-art battery, you should run it through the new process to make sure that the new process doesn't give you improved performance over the existing process used to make the battery. If you're looking at new formulations through a new process, you would run those against a control through the same set of conditions. So all this is based on the control. If you don't run a control, your experiment is worthless because you don't know if you're making improvements or not based on your control, based on your performance, or faulty equipment or a faulty experiment. And one more thing is you're going to have to make multiple replicates of each process condition to get some type of accuracy and reliability factor. Once you've completed your initial experimentation step, you're going to take that data and analyze it. And what you are looking for here is do you see any trends between the input variable and the output variable? And do those trends support or negate my hypothesis? So let's go back to the orange juice problem. Let's say your hypothesis is the larger I make the orange diameter, the sweeter the juice, right? So in your experimental plan, you've measured several diameters of oranges and then squeezed juice from them and then tested the sweetness of those individual juices squeezed. So now, does the data support the trend, or does the data show a trend between diameter size of orange and sweetness, right? If that trend does exist, does the trend support your hypothesis? Or does it negate your hypothesis? For example, you might say that the larger orange gives you the sweeter juice, when in fact the larger orange gave you the more sour juice, right? So you've learned something in there. You've learned that your hypothesis was wrong, but you've also learned now that maybe it's the reverse of what your hypothesis was. Do you need to do more experimentation? I don't know. But this is a step where you would find out by doing the analysis whether or not your analysis and your data is strong enough to support your hypothesis and therefore your conclusion. All right. You may have to refine your hypothesis, or you may have to refine your experimental plan to be able to better answer or better support your hypothesis or answer the question. And our last step is you have to basically then ask the question to yourself, was your hypothesis correct? Again, and what did you learn from your experiments? Your hypothesis may not have been correct, and most of the times it's not 100% correct. So you might have to go back and reconstruct your hypothesis to better explain what your observations were. Or you might have to go back and ask another question for further clarification. And then once you've done all this, right, you need to report all your results so that can be critiqued by fellow scientists, right? You may have missed something in your experiments. You want to make sure your experiments aren't biased to give you results that are not really representative of what really does happen, right? So you want to make sure that when you report results, you state exactly how you did your experiments and how you measured things as detailed as possible. So more detail is better, right? So for example, if you were running an experiment and you didn't control the humidity in the environment, and humidity was determined someplace else in the literature to be critical, then you might have to go back and now control humidity to get better responses for your set of conditions. It all depends on what your questions are. So let's not dwell too much on that. But basically, did your experiment support your hypothesis? If it did, great. If it didn't, what did you learn, and what would you do? Should you amend your hypothesis to better address your observations? Okay, if you've been following my self-help videos, you know at this point we have like a self-check. And it's no different here. So there are questions on the left-hand side that you're going to answer and put your responses in the right-hand side column. Now, you're not going to do this in the video. You're going to write the answers down or write the questions down on a separate piece of paper and then answer them. And when you're ready for the answers in the video, you're going to restart the video. So now is when you stop the video, copy the information down, answer the questions, and then restart the video when you're ready. So stop the video now. Okay, here are the answers that I came up with, and I'm not going to spend a lot of time on this because you can read as much as I can. So let's just quickly go through this. The step that we do, the scientific method where data is taken, is our experimental step, right? Adding a water to an unknown solid turns the water yellow is an observation, so that would lead to your question at some point, like why does that happen? Graphs and tables are typically constructed and used in the analysis section, right? And then which step would you make the following statement? If I add hydrochloric acid to zinc solid, I make an explosive gas. That's our hypothesis. It's an if-then statement. You remember if, and then. The then is missing here, but it's implied. And that's our hypothesis. Peer review of our results and reporting are done during the reporting step. And then background research is done when we look for previous work in the literature to try and help us solve our problem or address our question. And hypothesis testing, again, is done in the experimental step. Our experiments are designed to test our hypotheses. So if you did well on these, great. You should consider yourself pretty up to speed on the scientific method. If not, you should go back and review some of the material I just talked about. Okay, so this is the end of the basic tutorial on the scientific method. Now you want to go to scientific method video number 2 if you struggled with getting a high percentage on the answers correct on the review slide. You want to learn a little bit more about the details of each step in the process, or you're required to by your instructor, right? If you have think that you have mastered the concept well enough that you need to move on, then this would be the end point of your instruction. Elsewise, look for the second part of the video, another video called Scientific Method number 2, and then start reviewing that one.